In this lecture, we are going to show that every Möbius transformation is the composition of a finite number of Euclidean isometries, dilations, contractions, and the reciprocal map. Before we proceed with the proof, we first describe what these different transformations of the complex plane are. Examples of Euclidean isometries include rotations, translations, and reflections. A rotation is usually associated with a fixed point, which is the axis of the rotation, and an angle theta by which every point on the plane is rotated around the axis point. For this exercise, we are setting the origin or the point O to be the axis of the rotation. We take the rotation to be counterclockwise when the angle of the rotation theta is positive. Let the corresponding rotation about the origin be r sub theta. If z is a complex number, r sub theta of z can be written as z times e raised to the power I times theta, where e raised to the power I times theta is equal to cosine theta plus I times sine theta, and corresponds to the point on the unit circle whose coordinates are cosine theta and sine theta. We can see clearly that this is the rotation that we have just described when we use polar representations. Every complex number z can be written in the form the absolute value of z times e raised to the power I times zeta, where the absolute value of z is the distance of z to the origin. If z equals x plus yi, where x and y are real numbers, then z corresponds to the point xy on the plane, and the distance of z to the origin, or the absolute value of z, is the square root of x squared plus y squared. Zeta, on the other hand, is the angle formed by the segment OC measured counterclockwise from the positive real axis. Zeta is also referred to as an argument of z and is written as arg parentheses z. Therefore, multiplying z by e raised to the I times theta power, we still add exponents when multiplying complex numbers. We get the absolute value of z times e with exponent I times the quantity zeta plus theta. So r sub theta of z has an angle which is theta more than zeta, so that z is rotated counterclockwise by an angle theta around the origin. Every translation on the complex plane is associated with a fixed complex number that we can also regard as a vector. We call this complex number or translation vector v. So if t sub v is the corresponding translation, then t sub v of z is z plus v. Under t sub v, a polygon such as the quadrilateral, whose vertices are the complex numbers a, b, c, and d, will have their vertices at t sub v of a, t sub v of b, t sub v of c, and t sub v of d. Each reflection on the complex plane is associated with a fixed line of reflection. We call this line of reflection L. The reflection of A across line L is the point A prime, such that the segment connecting A and A prime is bisected by line L, and not only that, L is also a perpendicular bisector of the segment. The same is true for the segment connecting B and its reflection B prime, the segment connecting C and its reflection C prime, and the segment connecting D and its reflection D prime. A dilation/contraction, in contrast to the other mappings, is not a Euclidean isometry since it changes distances between points unless it is the identity map. Each dilation/contraction is associated with a fixed positive real number u. If m is the associated dilation/contraction, then m of z equals u times z, which is equal to u times the absolute value of z times e raised to the power I times zeta. If u is greater than 1, the distance of z to the origin is stretched by a factor u under the map m. If, on the other hand, u is less than 1, the distance of z to the origin shrinks by a factor u so that we have a contraction. We generalize this to include the case where u is a negative real number or just a plain generic non-zero complex number. We write u in the form the absolute value of u times e raised to the power I times omega, where omega is an argument of u. And so u times z equals the product of the absolute values of u and z times e raised to the power I times the quantity omega plus zeta. What we have is a mapping that is a composition of a rotation with a dilation/contraction. Let's call this map RDC. We have the last mapping pertinent to this exercise, and this is the reciprocal map, which we designate as the map R. As the name suggests, R of z is simply 1 over z. By multiplying both numerator and denominator by the conjugate of z over itself, we find that 1 over z equals the conjugate of z divided by the square of the absolute value of z. The conjugate of z, which is x minus y times I, is the reflection of z across the x-axis or the real axis. Divide the conjugate by the square of the absolute value of z and we get a point that is on the ray through the conjugate with the origin as the initial point. Related to the reciprocal point, but should not be confused with, is the inversion point of z with respect to the unit circle. If z is not equal to 0 and z star is the inverse point of z with respect to the unit circle, then z star is the point on the ray through z with the origin as the initial point, so that the product of the absolute values of z and z star equals 1. One can verify as an exercise that z star is the conjugate of the reciprocal point of z, which also makes it the reciprocal point of the conjugate of z. So now we're ready to tackle the proof of the theorem. If f is a Möbius transformation, then f of z can be written as the quantity a times z plus b divided by the quantity c times z plus d, where a, b, c, and d are complex numbers, with the discriminant ad minus bc not equal to 0. We break down the proof into two cases. We have either c is 0 or c is not equal to 0. If c equals 0, since AD minus BC is not equal to 0, then A and D are both non-zero. So f of z equals A over d times c plus b over d, which we rewrite as A over d times the quantity z plus b over a. Let g of z be equal to z plus b over a, so that we have a translation by the vector b over a. Let h of z be equal to a over d times z, so that we have a rotation, dilation/contraction. We check that h of g of z equals f of z. G of z is z plus b over a. To apply h to this, we multiply by a over d to get f of z, which proves the theorem for case 1. For the second case, when c is not equal to 0, we carry out some sort of manual long division on f of z. We spread out the numerator. We multiply by c and divide by c. Then we add ad in the numerator and subtract ad. This part simplifies to a over c. We rewrite the rest of f of z as the quantity bc minus ad divided by c times the reciprocal of cz plus d. We take out c from cz plus d, and further rewrite this last bit as the quantity bc minus ad divided by c squared times the reciprocal of z plus d over c. And now we decompose f. We have the translation t sub d over c, where t sub d over c of z is z plus d over c. Then we have the reciprocal map R of z. Then it's a rotation dilation / contraction map RdC of z, which is equal to the quantity bc minus ad divided by c squared times z. Finally, we have another translation with translation vector, this time a over c. T sub a over c of z equals a over c plus z, or z plus a over c. We now verify that f of z equals t sub a over c of r dc of r of t sub d over c of z. T sub d over c of z is z plus d over c. R applied to this gives us the reciprocal of z plus d over c. RdC applied to this multiplies the quantity bc minus ad divided by c squared to this reciprocal. T sub a over c translates this last expression, giving us f of z.